Have you ever heard someone use the word momentum and wondered what it meant? The term itself can be used in several contexts, but in terms of physics, momentum refers to a measurement involving when an object of a certain mass is in motion.
This measurement can be displayed by the equation which states that momentum is equal to mass times velocity. In variables, p equals m times v, where p is momentum, m is mass, and v is velocity. This equation gives us the linear momentum possessed by an object in question.
Therefore, in real-life situations, any object that possesses mass and is in motion can have its linear momentum measured. What happens, however, when multiple objects collide together? Are their values of momentum constant or changing?
The answer to that question lies within the concept of conservation of momentum. Assuming that there are no outside forces acting on a system, which is a very important part for this concept to hold true, the total momentum of a system is conserved. The amount of momentum possessed initially in a system should be equivalent to the amount of momentum present after any collision.
With conservation of momentum established, we can now measure momentum in the cases of collisions. An important thing to bring up now would be the different types of collisions that occur. First off, there are cases of collisions in which both momentum and kinetic energy are conserved. All objects involved in the collisions maintain their original form and remain separated in the end. This type of collision is called an elastic collision. One important thing to note is that both momentum and kinetic energy, again, are conserved in this type of collision. Let's take a look at a real-life example. So now we're going to show you a real-life example of an elastic collision using this. 1, 2, 3. That was fun. Now that we have a visual aid for the process, let's work on a created example to show how we calculate answers involving conservation of momentum. Okay, to begin with, I have written down the formula that we are going to use in order to solve conservation of momentum with regards to an elastic collision. The formula reads m1 times v1 in the initial stage of the problem plus m2 times v2 in the initial stage of the problem is equal to m1 times v1 in the final stage of the problem plus m2 times v2 in the final stage of the problem. Now, for this example, we are going to say that object 1 has a mass of 10 kilograms and is traveling at a velocity of 5 meters per second in the positive eastward direction. Now, we are also going to say that object 2 has a mass of 5 kilograms and is traveling 4 meters per second in the westward direction. Now, since we established that the eastward direction is positive, that means westward must be negative. Therefore, the initial velocity of object 2 should be negative 4 meters per second. Now, we're given the final velocity of object 2, which is positive 7 meters per second. If we think about that conceptually, what that means essentially is that the object rebounded off of object 1 and is now traveling in the positive eastward direction itself. Now, what we're looking for is the final velocity of object 1. Well, based on all the information we're given, we can plug into the formula and solve from there. After we plug values into our formula, it should now read 10 kilograms times 5 meters per second plus 5 kilograms times negative 4 meters per second is equal to 10 kilograms times the velocity we're looking for plus 5 kilograms times 7 meters per second. And now, it's worth noting that kilograms times meters per second is the unit we use to represent momentum. So now, in the end, we should get 50 kilograms times meters per second minus 20 kilograms times meters per second is equal to 10 kilograms times the velocity we're looking for plus 35 kilograms times meters per second. What we can do now now we can subtract the 20 from the 50, and we're left with 30 kilograms times meters per second is equal to 10 kilograms times the velocity we're looking for, plus 35 kilograms times meters per second. We now subtract the 35 over, and we get negative 5 kilograms times meters per second is equal to 10 kilograms times the velocity we're looking for. To find our final solution, we can divide the 10 over under the negative 5, and we're left with an answer of negative 0.5 meters per second for our final velocity with regards to object 1. Notice that in this collision, both bodies start off separately and remain separately in the end. This supports the idea of an elastic collision. However, just because two objects remain separate does not mean that they are always part of an elastic collision.
Generally, if the collision is not considered elastic but is between objects colliding, then it is considered inelastic. An inelastic collision occurs when two objects collide and the momentum is conserved but the kinetic energy of the two objects is not, because some of that kinetic energy is often converted into another type of energy as the collision occurs. If the two objects stick together after the collision, then it is considered perfectly inelastic. Now we're going to show you a real-life example of an inelastic collision using this.
1, 2, 3.
Here we have the formula for a perfectly inelastic collision. Mass 1 times the initial velocity of mass 1 plus mass 2 times the initial velocity of mass 2 equals mass 1 plus mass 2 times the final velocity. And for this instant, we'll be using these formulas. So for mass 1, we'll be using 7 kilograms. The initial velocity of mass 1 will be using 2 meters per second. Mass 2 will be using 3 kilograms. The initial velocity for mass 2 will be using 0 meters per second. And we'll be trying to figure out the final velocity. So when you plug in the values to their corresponding places, you'll get these values. 7 kilograms times 2 meters per second plus 3 kilograms times 0 meters per second equals 7 kilograms plus 3 kilograms times the final velocity. When you simplify that, we get 14 kilograms meters per second plus 0 kilograms meters per second equals 10 kilograms times the final velocity. When we simplify that further, we get 14 kilograms times meters per second equals 10 kilograms times the final velocity. And when we simplify that again, we get our answer 1.4 meters per second for the final velocity.
Well, that just about does it for our brief explanation of linear conservation of momentum. If you're still interested with regards to the subject, there will be a link provided to a page on the NASA website that does a great job of explaining the linear conservation of momentum as a whole and providing a good example of it. In comparison to the explanations and examples we provided in our video, the NASA page is a bit more complex as it starts getting involved with gases and pressure and stuff such as that. However, the general ideas are still there, and therefore it is a great resource to utilize.